Moving on to our second objective here, which is to understand the partial pressures that exist in the alveoli and the blood, and then consequent effect on gas exchange. So we'll talk about gas exchange, which happens in the lungs. It also takes place down at the level of the respiring tissue. So think about the mitochondria, think about the oxidative phosphorylation that's using this oxygen, and think about our cells that are also producing this CO2 as a byproduct. And so we see gas exchange happening at the lungs, but also down at the level of our respiring tissues. And then finally, we'll speak about the determinants of alveolar partial pressure, as well as the alveolar partial pressure of CO2. So oxygen and CO2 partial pressures. Okay, now in order for a gas to diffuse, it's going to need a gradient. Okay, gradients are kind of this universal law that we see throughout our physiology. We talked about it in the circulatory system. We talked about it as it applies to bulk flow and air movement. And we speak about it here as well in terms of these gases moving more at a cellular and subcellular level. And so gases always diffuse down their pressure gradient from high pressure to low pressure. And if we look even further, a gas in a mixture diffuses in the same manner. So it's going to move down its high partial pressure to its low partial pressure. It's going to move down its partial pressure gradient. Okay. In other words, if I'm thinking about oxygen as a part of this mixture of gas, the movement of oxygen is only influenced by the partial pressure of oxygen. So oxygen will move from a place of its high partial pressure to a place of low partial pressure, and it will not be influenced by the partial pressure of the other gases that are also in that mixture. All right. And so we really want to think about the individual partial pressures, where they're the highest and where they are the lowest, in terms of figuring out the direction of movement of these gases individually. And this is why these gases move independently. This is why oxygen moves in one direction, CO2 moves in another direction, because they are moving or honoring their own partial pressure, moving along, or honoring their own partial pressure gradients, and they are completely ignoring the partial pressures of the other gases that are also in that mixture. All right. So if we think about that, we can then look at the oxygen cascade. And this is basically thinking about how the partial pressure changes as we move from the atmosphere into the alveoli, through our systemic arteries, down to the level of our cells and tissues here, at the level of systemic capillaries, and then back in the opposite direction, okay? And so we can see that the partial pressure of our gases is changing, and it's changing such that we have a gradient. So we go from a high partial pressure of oxygen in the atmosphere. It slightly reduces as we get down into the alveoli, so it goes from 160 to 100, and we talked about why this is. Because of the fact that we introduce humidity, we introduce moisture, we're going to see a reduced partial pressure of oxygen as we go from the dry air in the atmosphere to the moist or humidified air in our alveoli. For the rest of the way down, it's pretty much consistent until we get to the cells and tissues at the level of the systemic capillaries. Here we see that the partial pressure is now about 40 millimeters of mercury, for oxygen that is. And that's because we now have the movement of oxygen from our capillaries into our cells and tissues. And so what I really want to point out is the gradient. We go from 160 down to 40. And so that is a gradient that drives oxygen from the atmosphere all the way down into our cells and tissues. And we can think about even further across the mitochondria, all the way into the electron transport chain, where it can be used for oxidative phosphorylation, okay? If we think about CO2 and the partial pressure of CO2, we also have a change. It's going from 0.3 millimeters of mercury in the atmosphere to 40 millimeters of mercury in the alveoli, and then it's pretty consistent, but then it's going to go from 40 millimeters of mercury in the alveoli all the way up to 46 millimeters of mercury at the level of the cells and tissues. Excuse me. And that's because this is the area that we have the highest amount of CO2 being offloaded from our cells and tissues into our systemic capillaries. And then it's basically going to go all the way back to our alveoli and then it's going to diffuse out into the atmosphere. And so again, thinking about the direction of our gradient, it's really high down here in the cells and tissues. It's at 46. It's a little bit lower here at the alveoli at 40, and then it's even lower out in the atmosphere. So we have a gradient in the opposite direction. We have a gradient that allows or, facilitates the movement of CO2 from our cells and tissues all the way through our alveoli and eventually out into the atmosphere. Okay, and this is what we mean by the partial pressure gradients of each of these gases moving independently and facilitating different movement for our different gases. All right, any questions at this point? Any questions at this time? Okay, so we're going to illustrate that here and kind of just add some more clarity here, and we'll talk about the oxygen cascade first, and then we'll speak about the CO2 cascade. So the oxygen cascade is basically how the partial pressure of oxygen changes as we move through different branches or different parts of our vasculature. And that is really just facilitating the movement of that gas in one direction. Right? So we're looking at the partial pressure of oxygen here in millimeters of mercury. And we're thinking about the atmosphere here on the left. And as we get further to the right, we're thinking about the mitochondria being the most distal location where oxygen is being consumed. So this is basically our location throughout the vasculature. And we go from atmosphere here on the left all the way to our mitochondria where that oxygen is being consumed. Okay. So we start out with the partial pressure of oxygen being way up here at 160 millimeters of mercury. Right, that's kind of what exists out in the air. And then when we get to the alveoli, it's going to significantly drop off. So up here is going to be our atmosphere. Right, 160 millimeters of mercury. By the time we get down to our alveoli, it's going to drop off to about 100 millimeters of mercury. So this is our alveolus or alveoli. It's dropped off to 100 millimeters of mercury. Okay, and just to kind of put a note here, which explains why, this is because of the humidification of air as it moves through the conducting zone. So air is humidified. As it moves through the conducting zone. And so that is the explanation for this large drop-off that we see between the atmospheric partial pressure of oxygen and the alveolar partial pressure of oxygen. Okay. So the alveoli all the way to the systemic arteries, the partial pressure remains at 100 millimeters of mercury. So let's actually put that in here. So from the alveoli all the way to our systemic arteries, we have that 100 millimeters of mercury. Okay. We then see another drop off as we get down to the cells and tissues at the level of the systemic capillaries. So we see another drop off here. And so this is at the level of our cells and tissues. In other words, our systemic capillaries. And here it's about 40 millimeters of mercury. Okay, and that is really owed to the idea that we are now offloading that oxygen into our cells and tissues. And so we talked about this idea. That was the whole premise of Henry's law, right? The proportional relationship between the number of gas molecules and the partial pressure. As we lose those gas molecules, our partial pressure decreases. Okay, so that explains the second drop off that we see here. And then we have one more slight drop off, which explains what happens when we go down into the mitochondria. So even lower in terms of the level of oxygen consumption here, this is the mitochondria, where we sometimes see partial pressures that are lower than 40 millimeters of mercury, but for the most part, they're at or lower than 40 millimeters of mercury. Okay, in other words, if we have a lot of oxygen consumption, so high metabolic demand, we can see a lower partial pressure than 40 millimeters of mercury, but for the most part, it's about 40 millimeters of mercury, typically. All right, so this basically presents this direction for our gradient moving from the atmosphere down to our mitochondria. So this is the direction of our gradient in terms of the partial pressure change. Okay, and so we can add a bit of a note over here just to describe what this means. The partial pressure of oxygen gradient favors the movement of oxygen from the atmosphere all the way down to the mitochondria. Okay. And so this is why oxygen is moving in this direction. All right, let's speak about the movement of carbon dioxide. So carbon dioxide is obviously going to move in the opposite direction, but let's kind of illustrate the differing partial pressures which explain why it moves in the opposite direction. Okay. All right, so again, starting out, so we're looking at the CO2 cascade.
Please try that again.
Oh gosh, I apologize. Alexa is eavesdropping on me. Okay, so we've got our partial pressure of CO2 here on the Y. And then we've got the direction or the location of movement here on the X as well. All right, so we're looking at our location down here once again. And we're going from the atmosphere all the way to our cells and tissues. Okay, so we're not going to the mitochondria because remember CO2 is not made in the mitochondria, it's just made in the cell as a byproduct. And so that's the difference between the final or the initial rather location here in terms of the direction of movement there. All right, so we're basically looking at starting off all the way here at 0.3 millimeters of mercury. This is the partial pressure of CO2 out in the atmosphere. So this is where we start. Okay. So this is the atmosphere, which is 0.3 millimeters of mercury. And then we increase by the time we get to the alveoli, right? There's much more CO2 that's in the alveoli that's coming from the respiring tissues. So by the time we get to the alveoli, we see an increase, significant increase to about 40 millimeters of mercury. Okay. Now we see a slight increase as well as we think about our systemic veins and pulmonary artery, okay? So this is where we have the mixing of that venous blood. So all of that blood that's coming back from our respiring tissues has that deoxygenated blood, which has a heavy concentration of carbon dioxide. And so once again, we see an increase here as we think about our systemic veins and pulmonary artery. Okay, which is about 46 millimeters of mercury. All right. And then the final drop off that we see, which is not much of a drop off, but just to explain the final destination of CO2 here, this is at the level of our systemic capillaries, which is basically the cells and tissues. Okay, and here we see that the partial pressure of CO2 can be greater than 46, but it usually is at around 46. So it can be greater than or at 46 millimeters of mercury. In other words, just like what we described before with oxygen, if there's higher metabolic demand or there's a higher mismatching of these gas production, we can see a greater partial pressure of CO2 if the tissues are offloading more CO2 than what is being produced. But typically it's about 46 millimeters of mercury. Okay, and so what we see is another gradient, right? We go from high partial pressure to low partial pressure, which influences the direction of movement of this gas. And so the gradient is going to be in the opposite direction this time. So this is our diffusion gradient of CO2, okay? And again, just to add a note here about what this means, the partial pressure gradient of CO2 favors the movement of carbon dioxide from cells out into the atmosphere. Okay. All right. And I'm actually going to flip-flop these arrows. Okay, they should be in the opposite direction. I apologize. So the direction of movement is from cells out into the atmosphere. Okay,